Article 240.21 requires a main overcurrent protection device at the service entrance for all services except those specifically exempted in exceptions A through G. If the situation does not fall under any of these exceptions, Article 240.21 does apply to the service. Article 230.90 specifies the requirements for service entrance equipment, which is defined in Article 100 as the equipment installed where the service conductors enter a building and provide the means for disconnecting and isolating the building from the service conductors. Article 230.90 does not explicitly require a main overcurrent protection device as part of the service entrance equipment. The apparent conflict between Articles 240.21 and 230.90 arises because Article 240.21 is more specific than Article 230.90. Article 240.21 pertains specifically to the requirements for overcurrent protection of services, while Article 230.90 provides general requirements for service entrance equipment. When there is a conflict between a general requirement and a more specific requirement, the more specific requirement prevails. Based on the principles of code interpretation, Article 240.21 takes precedence over Article 230.90. Therefore, a main overcurrent protection device is required to be installed at the service entrance. This requirement applies regardless of the distance from the transformer secondary to the service disconnect. In electrical installations, ensuring safety and code compliance is paramount. When dealing with service entrances, understanding the nuances of the National Electrical Code, or NEC, is crucial. Two articles, 230.90 and 240.21, often come into play and can sometimes appear to conflict, leading to confusion. This narration will clarify these articles and explain why, in many cases, Article 240.21 takes precedence. Let's begin by examining Article 230.90. This section of the NEC deals with service entrance equipment. Service entrance equipment, as defined in Article 100, includes the necessary components installed where service conductors enter a building. These components facilitate the disconnection and isolation of the building from the service conductors, providing a critical safety measure. Article 230.90 outlines the general requirements for this equipment but does not explicitly mandate a main overcurrent protection device as a standard part of the service entrance. Next, we turn to Article 240.21. This article is more specific, focusing on the overcurrent protection of services. It generally requires a main overcurrent protection device at the service entrance for all services, with some specific exceptions outlined in subsections A through G. These exceptions typically cover very specific scenarios, such as certain types of industrial installations or services with unique configurations. Now, let's address the apparent conflict. The confusion arises because Article 230.90 provides general guidelines for service entrance equipment, while Article 240.21 zooms in on the specific requirement for overcurrent protection. In situations where a general requirement clashes with a more specific one, the more specific requirement usually takes precedence. This principle is a cornerstone of code interpretation. To illustrate this, consider a scenario where a building is supplied by a utility-owned transformer located outdoors. The secondary conductors from the transformer run a considerable distance, say over 25 feet, directly into the building. The service entrance equipment is situated immediately inside the building at the point of entry and is owned by the customer. In this case, Article 230.90 might suggest that a main overcurrent protection device is not strictly required as part of the service entrance equipment. However, Article 240.21 steps in, stating that unless one of the exceptions A through G applies, a main overcurrent protection device is indeed necessary. Since the given scenario typically does not fall under any of these exceptions, Article 240.21 prevails, mandating the installation of a main overcurrent protection device. The reasoning behind this precedence is rooted in safety. Overcurrent protection is a critical aspect of electrical system design. It safeguards against faults, overloads, and short circuits, which can lead to fires, equipment damage, and potential harm to people. Article 240.21 is designed to ensure that all services have adequate overcurrent protection right at the point of entry, minimizing the risk of electrical hazards within the building. It is important to understand that the distance from the transformer secondary to the service disconnect does not negate the requirement under Article 240.21. Regardless of the length of the service conductors, the main overcurrent protection device is still needed to protect the building's electrical system. To ensure code compliance and safety, it is always advisable to consult with a qualified electrical engineer or inspector. These professionals can assess the specific details of the installation, verify which code articles apply, and provide guidance on selecting and installing the appropriate overcurrent protection devices. Here are some additional points to consider. Firstly, the size and type of the main overcurrent protection device must be carefully selected based on the calculated load of the building and the ampacity of the service conductors. Secondly, the overcurrent protection device should be readily accessible and properly labeled for easy identification and maintenance. Thirdly, regular inspections and testing of the overcurrent protection devices are essential to ensure their continued functionality. Furthermore, any modifications or upgrades to the electrical system should be reviewed to confirm that the overcurrent protection remains adequate. In summary, while Article 230.90 provides general guidance on service entrance equipment, Article 240.21 specifically addresses overcurrent protection requirements. When there is an apparent conflict between these two articles, Article 240.21 typically takes precedence, mandating the installation of a main overcurrent protection device at the service entrance. This requirement is driven by the paramount need to protect the building's electrical system and ensure the safety of its occupants. Always prioritize safety and compliance with the NEC and consult with qualified professionals when in doubt. In addition to the previously mentioned NEC articles, it's important to understand the broader context of service entrance design and overcurrent protection. The service entrance is the critical point where electrical power is delivered from the utility to the building's electrical system. It includes service conductors, metering equipment, and the service disconnecting means. The service disconnecting means, often a main breaker or fuse disconnect, is the primary way to isolate the building from the utility power supply for maintenance, repairs, or emergencies. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of electricity when a fault or overload condition occurs. This protects conductors and equipment from damage due to excessive current. Overcurrent protection devices have two main characteristics that are important to understand. Firstly, ampacity, which is the maximum current a device can carry continuously without tripping or blowing, and secondly, interrupting rating, which is the maximum fault current the device can safely interrupt without failing. Selecting the appropriate overcurrent protection devices requires careful consideration of the calculated load of the building, the ampacity of the service conductors, and the available fault current at the service entrance. The calculated load is determined by adding up the power requirements of all the electrical equipment and appliances that will be connected to the electrical system. The ampacity of the service conductors must be sufficient to carry the calculated load, with appropriate diluting factors applied for ambient temperature and other conditions. The available fault current is the amount of current that would flow in the event of a short circuit. This value is typically provided by the utility company. The overcurrent protection devices must have an interrupting rating that is equal to or greater than the available fault current to ensure they can safely interrupt a fault. In addition to the main overcurrent protection device at the service entrance, branch circuit overcurrent protection is also required throughout the building's electrical system. Branch circuits supply power to individual outlets, lighting fixtures, and appliances. Each branch circuit must have its own overcurrent protection device, typically a circuit breaker or fuse, to protect the circuit conductors and connected equipment. The size of the branch circuit overcurrent protection device is determined by the ampacity of the branch circuit conductors. The NEC provides detailed tables and guidelines for selecting the appropriate conductor sizes and overcurrent protection devices for various applications. Proper overcurrent protection is essential for preventing electrical fires, equipment damage, and electrical shock hazards. It is a critical component of a safe and reliable electrical system. Therefore, it is important to understand the requirements of the NEC and to consult with qualified electrical professionals when designing, installing, or modifying an electrical system. Let's delve deeper into the specific requirements of Article 240.21 and its exceptions. As previously mentioned, Article 240.21 generally requires overcurrent protection at the point where the service conductors are considered to be supplied. This is often at the service entrance. However, there are several exceptions to this rule outlined in subsections A through G. Understanding these exceptions is crucial for determining whether a main overcurrent protection device is truly required in a specific situation. Exception A covers installations where the service conductors are not more than 10 feet long, are enclosed in a raceway, and terminate in a single overcurrent device that limits the load to the ampacity of the conductors. This exception is typically used for short service drops from a transformer to a service disconnect located nearby. Exception B applies to installations where the service conductors are not more than 25 feet long and are protected from physical damage. In this case, the overcurrent protection can be located at the termination point of the conductors, provided that the ampacity of the conductors is at least 1/3 of the rating of the overcurrent device. This exception is often used for services where the transformer is located relatively close to the building. Exception C covers installations where the service conductors supply a fire pump. Fire pumps are critical for fire suppression and must be able to operate reliably even under fault conditions. Therefore, the NEC allows for the overcurrent protection to be located further away from the service entrance, provided that certain conditions are met. Exception D applies to installations where the service conductors supply emergency systems. Similar to fire pumps, emergency systems must be able to operate reliably during power outages and other emergencies. The NEC allows for some flexibility in the location of the overcurrent protection for these systems. Exception E covers installations where the service conductors supply legally required standby systems. Legally required standby systems are systems that are required by law to provide power during power outages, such as life safety systems in hospitals. The NEC allows for some flexibility in the location of the overcurrent protection for these systems, similar to emergency systems. Exception F applies to installations where the service conductors supply critical operations power systems. Critical operations power systems are systems that are essential for maintaining critical operations in facilities such as data centers and hospitals. The NEC allows for some flexibility in the location of the overcurrent protection for these systems, similar to emergency systems. Exception G covers specific installations involving multiple service disconnects. This exception is complex and requires careful analysis to determine if it applies to a particular situation. It is important to note that these exceptions are very specific and must be carefully evaluated to determine if they apply to a given installation. If none of these exceptions apply, then Article 240.21 requires overcurrent protection at the service entrance. In addition to understanding the exceptions to Article 240.21, it is also important to understand the requirements for the location and accessibility of the service disconnecting means. The service disconnecting means must be located at a readily accessible location either outside of a building or structure or inside nearest the point of entrance of the service conductors. The disconnecting means must be suitable for use as service equipment and must be legibly marked to indicate its purpose. The disconnecting means must be capable of being locked in the open position. This allows for the service to be safely disconnected for maintenance or repairs. The disconnecting means must be readily accessible to qualified personnel. This ensures that qualified personnel can quickly disconnect the service in the event of an emergency. The location of the service disconnecting means is a critical safety consideration. It must be located in a place where it can be easily accessed in an emergency, but it must also be protected from unauthorized access. The disconnecting means must be installed in accordance with the manufacturer's instructions and the requirements of the NEC. The NEC provides detailed requirements for the installation of service equipment, including the service disconnecting means. These requirements are designed to ensure the safety and reliability of the electrical system. It is important to follow these requirements carefully when installing service equipment. Let's discuss the practical implications of these code requirements in real-world scenarios. Consider a situation where a new commercial building is being constructed. The building will be served by a 480/277 volt, 3-phase service. The utility transformer is located outdoors approximately 50 feet from the building. The service conductors will be run underground from the transformer to the building. In this case, Article 240.21 will likely require a main overcurrent protection device at the service entrance. None of the exceptions to Article 240.21 are likely to apply, as the service conductors are longer than 25 feet and are not supplying a fire pump, emergency system, or legally required standby system. Therefore, a main breaker or fuse disconnect will need to be installed at the service entrance to protect the building's electrical system. The size of the main overcurrent protection device will need to be carefully selected based on the calculated load of the building and the ampacity of the service conductors. The overcurrent protection device will also need to have an interrupting rating that is equal to or greater than the available fault current at the service entrance. The service disconnecting means will need to be located at a readily accessible location inside the building, nearest the point of entrance of the service conductors. The disconnecting means will need to be suitable for use as service equipment and will need to be legibly marked to indicate its purpose. The disconnecting means will also need to be capable of being locked in the open position. Now consider a different scenario where a small residential building is being served by 120/240 volt single-phase service. The utility transformer is located on a pole approximately 15 feet from the building. The service conductors will be run overhead from the transformer to the building. In this case, exception B to Article 240.21 might apply. If the service conductors are protected from physical damage and the ampacity of the conductors is at least 1/3 of the rating of the overcurrent device, then the overcurrent protection can be located at the termination point of the conductors, which may be at the meter or at a panel board inside the building. However, it is important to carefully evaluate the specific requirements of exception B to ensure that all conditions are met. If the conditions of exception B are not met, then a main overcurrent protection device will need to be installed at the service entrance. These examples illustrate the importance of understanding the specific requirements of the NEC and carefully evaluating each installation to determine the appropriate overcurrent protection. Always consult with qualified electrical professionals when designing, installing, or modifying an electrical system. In addition to the NEC, local codes and regulations may also apply to electrical installations. It is important to be aware of these local requirements and to comply with them. Local codes may be more stringent than the NEC in some cases. For example, some local codes may require a main overcurrent protection device at the service entrance regardless of the length of the service conductors. It is important to check with the local electrical inspector to determine the applicable local codes and regulations. Electrical inspections are typically required for new electrical installations and for modifications to existing electrical systems. The purpose of the electrical inspection is to ensure that the electrical system is installed in accordance with the NEC and local codes. The electrical inspector will review the plans for the electrical system and will conduct a visual inspection of the installation. If the electrical system is found to be in compliance with the codes, the inspector will issue an approval. It is important to obtain an electrical inspection approval before energizing a new electrical system or modifying an existing system. Energizing an electrical system without an inspection approval can be dangerous and can result in penalties. Working with electricity can be dangerous. It is important to take precautions to protect yourself from electrical shock and other hazards. Always disconnect the power before working on electrical equipment. Use insulated tools and wear appropriate personal protective equipment, such as safety glasses and gloves. If you are not comfortable working with electricity, hire a qualified electrician. Qualified electricians have the training and experience to safely install and maintain electrical systems. They are also familiar with the NEC and local codes. Hiring a qualified electrician can help to ensure that your electrical system is safe and reliable. In conclusion, understanding the requirements for service entrance overcurrent protection is critical for ensuring the safety and reliability of electrical systems. Article 240.21 of the NEC generally requires overcurrent protection at the service entrance, but there are several exceptions to this rule. It is important to carefully evaluate each installation to determine if any of the exceptions apply. Always consult with qualified electrical professionals when designing, installing, or modifying an electrical system. By following these guidelines, you can help to ensure that your electrical system is safe and in compliance with the NEC and local codes.